Hi, in this video I'm going to talk about the impulse signal or impulse function, or there are other names like the Dirac delta function or delta function. Now, the signal, the impulse signal is a rather peculiar signal in the following sense. It is in fact a singular function. Okay, before seeing the details of the impulse function, let us start with the following pulse signal or pulse function, which will be denoted by x a of t. And it's defined as follows. It is equal to 1 over a for t between minus a over 2 and plus a over 2 and 0 otherwise. Okay, so this is a rectangular pulse signal with the following graph: xa of t. Now the magnitude of the signal over the interval where it is non-zero, which is namely from minus a over 2 to a over 2, the magnitude is equal to 1 over a. Okay. Now it is clear that for any value of a, of course here a is a positive real value, real number. Now for any a, we have such a rectangular pulse, and it is clear that the integral of this xa of t is equal to 1. That means the area under the rectangular pulse is equal to unity. Now, what happens if a gets smaller in value? Now, as a gets smaller, as you see, the duration of the pulse will get shorter and the magnitude will get larger. Okay? So we will have such a picture for larger values of smaller values of a, so it will be a very short duration pulse from minus a over 2 to a over 2, and of course 1 over a will be large. So this is for small a, the picture for small a. Now it is clear that although a gets smaller and smaller, still the area under the pulse is equal to 1. And we are going to claim that in the limit as a tends to 0, this rectangular pulse will tend to a rather peculiar signal with 0 duration and infinite magnitude. Located at t equal to 0, the magnitude will be equal to infinity, which is quite meaningless. That means we have in fact a divergence phenomenon in this case, 0 duration and infinite magnitude. So that is in fact called an impulse. As a tends to 0, So as a tends to 0, xa of t will tend to delta of t. Now, the symbol we use for the impulse signal is delta of t. So this delta of t is called the impulse function or signal in signal theory. But there are other names in the literature. The delta function or Dirac delta function are also familiar names for this rather peculiar signal. Now, the graphical representation for the impulse is as follows. The impulse signal delta of t is denoted by such an arrow just to show that it tends to infinity at t equal to 0. So this is t equal to 0 point on the horizontal axis. And just we place this 1 in brackets beside this representation of the impulse to show that its strength, or in other words, the area under the curve, the integral, is equal to 1. So from minus infinity to plus infinity, delta of t integrated with respect to t is equal to 1. Okay, so this is how we introduce the impulse signal or impulse function. Sometimes it is called the unit impulse function or unit impulse signal because of the fact that this integral is equal to unity. For instance, if instead of defining xa of t as 1 over a in the interval from minus a over 2 to a over 2, we can start with, for instance, 5 over a. So in that case, the integral will be equal to 5. And that will be the strength of the impulse. And instead of 1 in the brackets, we are going to write down 5 for the strength of the impulse. So this is called the strength of the impulse. Okay, the impulse signal is, of course, a physically non-realizable signal. Therefore, it's a mathematical entity. And in terms of the mathematical representation, still we have some problems. For example, what do we mean by zero duration and infinite magnitude? So such a definition is not very meaningful in terms of rigorous mathematics. So there are other ways to handle this impulse function or the Dirac delta function, and the theory developed for understanding such singular functions is known as the theory of distributions, but we are not going to discuss that topic in this video. So the impulse signal is defined in terms of the, I'm saying in quotations, limit of such a rectangular pulse as the duration of the pulse tends to 0 and the magnitude of the pulse tends to infinity at the same time. Now, in signal theory, the impulse signal is important because of its certain properties. Now, in order to understand why it's important, we have to discuss the product of the impulse with an arbitrary function and then the integral of that product. Okay, in order to understand the importance, we have to look at such operations. So, now, after discussing the meaning of the impulse signal, let x of t be an arbitrary signal or function. So x of t will be completely arbitrary like this. Okay, then the product of x of t with, for example, xa of t will be as follows. X of t times xa of t will be approximately equal to x of 0 divided by a for t between minus a over 2 to a over 2, and it will be 0 otherwise. Now, this approximation is valid under the condition that a is sufficiently small. So if it is a short duration pulse, of course, that meaning of the short duration depends on the behavior of x of t around t equal to 0, but it is clear that when you multiply x of t with the rectangular pulse, approximately the result will be the value of x of t at 0 times the magnitude of the pulse, which is equal to 1 over a. Okay? Then, if we integrate x of t times xa of t from minus infinity to plus infinity, this will be approximately equal to x of 0. Okay? Of course, this approximation is valid for sufficiently small values of a. Okay, so how can we now generalize this operation to the product of the signal with the impulse? So it is clear that x of t times delta of t is equal to x of 0 delta of t. Now why? Because delta of t is 0 for all values of t except t equal to 0. Therefore, only the value of x of t at t equal to 0 will be taken into account. And therefore, the integral of x of t times delta of t with respect to t will be equal to the integral of x of 0 delta of t. Now x of 0 is a constant, therefore it can be taken outside of the integral, and the remaining integral is the integral of delta of t with respect to t. Now this is equal to 1, and we get x of 0. Now this is the so-called sampling property of the impulse. That means the impulse samples the signal x of t at t equal to 0, at the instant where the impulse strikes. Okay. Now, let us look at the shifted impulse. Now remember, the impulse delta of t is 0 for all values of t except the value t equal to 0, where it has an infinite value or a singular behavior. Now delta of t minus t0 is the shifted impulse. It is the impulse signal shifted by amount t0. So the graphical representation for the shifted impulse will be the following. Here we have the impulse. Now the impulse strikes at t equal to t0, and again the strength of the impulse is equal to 1. Okay, now what about the product of x of t with delta of t minus t0 for an arbitrary signal x of t? So again, x of t is an arbitrary signal. X of t times delta of t minus t0 is x of t0 delta of t minus t0, right? Because delta of t minus t0 is 0 everywhere except t equal to t0, where it has infinite magnitude. Therefore, the value of x of t can be replaced by x of t0. And it is clear that the integral of x of t times delta of t minus t0 integrated with respect to t is equal to x of t0. This is again the sampling property of the impulse. Now the shifted impulse. Okay, so as a summary, the impulse signal is not one of the well-behaved signals like the cosine signal, sine signal, or the pulse signal, etc. But it is a rather peculiar signal which is 0 for all values of 0 except a single time instant. Therefore, it has 0 duration. And at that time instant, it has infinite magnitude, such that still the area under the singular pulse, which is named as the impulse, is equal to unity. Okay. Now, in signal theory, the variable t is interpreted as time, and therefore delta of t is defined in terms of a function of time, which is a pulse with 0 duration and infinite magnitude. But there are other examples where we use impulses in space. So delta of t is impulse in time. But for instance, as a function of space, how can we visualize or how can we associate a meaning to the Dirac delta function or impulse function? Well, look at the following case. Suppose that we have a point charge located at the origin in a three-dimensional space. So this is our space, so 3D space, and here at the origin we have a point charge Q. Point charge at okay, let us show the coordinate vector as capital R equal to 0. So the charge density at that location is in fact infinite. Why? Because we have a charge of amount Q in zero volume. Therefore, the charge is compressed to zero volume, meaning that the charge density rho of R is equal to Q times delta of R. Okay? So this delta of R is now an impulse in space. Or let us call it the Dirac delta function now. In space. Again, if you integrate the charge density over the entire space, okay, let us call this R3, so you are going to have the volume integral over the entire space of Q times delta of R with respect to an integration with respect to the volume element dV. So it will be equal to Q because the integral of delta of R will be equal to 1. Because delta of R is defined as 0 everywhere except the origin where it is infinite in magnitude. But still the integral is finite and we have the integral equal to 1. Okay, so we have in this video we have seen the Dirac delta function or impulse function or delta function. There are these names are used interchangeably in the literature, both in signal theory as a signal, as a pulse with zero duration and infinite magnitude, and we have seen that in some other applications we may encounter the versions in space. That means a space function which is zero everywhere except at a single point. It is not finite, it has an infinite magnitude, like the case of a point charge example. So that's all I want to say about the unit impulse. Thanks.